students, in this video we are going to see Cauchy sequences. Cauchy sequences. First we see definition. A sequence in a metric space XD, in a metric space XD is said to be Cauchy sequence. Cauchy sequence is said to be Cauchy sequence if for each epsilon is greater than 0 there exists a positive integer n such that d of xn comma xn strictly less than epsilon for all m comma n is greater than or equal to capital N. A sequence in a metric space XD is said to be Cauchy sequence if for each epsilon greater than 0 there exists a positive integer n such that d of xm comma xn is strictly less than epsilon for all m comma n is greater than or equal to capital N. Okay. We will see one theorem. Every convergent sequence Xn in a metric space XD is Cauchy sequence. Okay. Let us see proof of this theorem. Proof is, let sequence Xn converges to X as n tends to infinity. Okay. Therefore, for each epsilon greater than 0, there exists a positive integer n such that d of xn comma x is strictly less than epsilon by 2 for all n is greater than or equal to capital N. Okay, and we have to show that this sequence Xn is a Cauchy sequence. Means we have to show that d of xn comma xn is strictly less than epsilon. So we will consider this LHS. Now d of xn comma xn, okay, which is less than or equal to. Here we will use triangle inequality. D of xn comma x plus d of xn x comma xn, since by triangle inequality. Okay, since by triangle inequality. This is triangle inequality. Okay, which is less than or equal to d of xn comma x plus d of xn comma x, because here d is symmetric, therefore d satisfies symmetry property, which is strictly less than d of xn comma x is strictly less than epsilon by 2, therefore d of xn comma x is also strictly less than by epsilon by 2 for all m comma n is greater than or equal to n, which is strictly less than epsilon. Therefore, d of xn comma xn is strictly less than epsilon for all m comma n is greater than or equal to n. Therefore, sequence xn is a Cauchy sequence. Therefore, sequence xn is a Cauchy sequence in capital X. Okay, proof is very simple. We have in this theorem we have to prove every convergent sequence xn in metric space xd is a Cauchy sequence. So we have taken xn converges to x as n tends to infinity. Here we use the definition of convergent sequence, and in next step we will use d of xn comma xn is less than or equal to d of xn comma x plus d of xn x comma xn by triangle inequality, which is less than or equal to d of xn comma x plus d of xn comma x, which is strictly less than epsilon by 2 plus epsilon by 2, which is strictly less than epsilon by 2. Therefore, d of xn comma xn is strictly less than epsilon for all m comma n is greater than or equal to n. Therefore, sequence xn is a Cauchy sequence in capital X. Okay. Let us take one remark. Remark is, in a metric space, every convergent sequence is Cauchy, but converse need not be true. That is, every Cauchy in a metric space, every Cauchy sequence need not be convergent. For example, let x is equal to semi-open, semi-closed, closed interval 0, 1 be the metric space with usual metric and sequence xn where xn is equal to 1 by n be a sequence in x. Okay, then sequence xn is a Cauchy sequence since for each epsilon greater than 0 we have d of xn comma xn is equal to mod of, here xn is 1 by m, so xn is 1 by m minus 1 by n, which is strictly less than epsilon, because here this x is a usual metric, means in usual metric d mod of d of xy is equal to, I will write here d of xy is equal to mod of x minus y. So here is d of xn comma xn is equal to mod of 1 minus m minus 1 upon n, which is strictly less than epsilon for all m comma n is greater than or equal to capital, here is for all m comma n is strictly less than 1 by epsilon. Okay. On the other hand, xn converges to 0 and that 0 does not belong to x. That 0 does not belong to x means here we get sequence xn in X, therefore sequence xn in capital X is a Cauchy but not a convergent sequence. A convergent sequence. Because xn converges to 0, but that 0 does not belong to X. So the sequence xn is not convergent in capital X. Note that if we take x is equal to closed interval 0 1, then the sequence xn is Cauchy as well as convergent. Cauchy as well as convergent. Let's take one theorem. Let sequence xn be a convergent sequence in a metric space XD such that xn converges to X as n tends to infinity if sequence xnk is any subsequence of sequence xn, then xnk converges to X as k tends to infinity. Okay. Let us see proof of this theorem. In this theorem we have given that sequence xn be a convergent sequence in a metric space XD such that xn converges to X as n tends to infinity. If xnk is any subsequence of sequence xn, then xnk converges to X as k tends to infinity. Okay. Let sequence xn be a convergent sequence such that xn converges to X as n tends to infinity. Okay. Therefore, for all epsilon greater than 0, there exists a positive integer n such that what d of xn comma x is strictly less than epsilon by 2. Okay. Let sequence xnk here already we have given, so here we say since sequence xn is a convergent sequence. Also we have given that sequence xnk is any subsequence of sequence xn. Also since sequence xnk is a subsequence of sequence xn, and we have to show that xnk is converges to X as k tends to infinity. Okay. d of xn k comma x. Now, which is less than or equal to d of xn k. Sorry, here is for all n is greater than or equal to capital N. D of xn k comma xn plus d of xn comma x. Okay. Call this equation number star. Okay. Since every convergent sequence in metric space xb is a Cauchy sequence. Therefore, sequence xn is a Cauchy sequence, because we have given that sequence xn is a convergent sequence in metric space xd. Is a Cauchy sequence. Okay. Therefore, by definition of Cauchy sequence, we have, therefore, for all epsilon greater than 0, there exists a positive integer. N such that d of xn comma xn is strictly less than epsilon for all n comma n is greater than or equal to capital N. Call this equation number. Suppose this is 1 and this is 2. Okay. Therefore, star becomes, equation star is d of xn k comma x, which is less than or equal to d of xn comma xn is strictly less than epsilon by 2. Therefore, d of xn k comma xn is also strictly less than by epsilon by 2 plus d of xn comma x is strictly less than epsilon by 2, which is equals to epsilon. Sorry, here is strictly less than epsilon. This implies xn k converges to x as k tends to infinity. Okay, in this theorem, we have to prove that if sequence xn k is any subsequence of sequence xn, then xn k converges to x. Since sequence xn is a convergent sequence, such that xn is converges to x. Here we use definition of convergent sequence. Also, since sequence xn k is a subsequence of sequence xn, here we will use triangle inequality. That is, d of xn k comma x is less than or equal to d of xn k comma xn plus d of xn comma x. Since every convergent sequence in a metric space xd is a Cauchy sequence, therefore sequence xn is a Cauchy sequence. Here we will use definition of Cauchy sequence. Here we can say that, therefore equation star becomes, and this is by 1 and 2, and we get xn k converges to x as k tends to infinity. Okay, hence proof of theorem is complete. Okay, let us take one remark. If a subsequence of a sequence in xd is convergent then the sequence itself need not be convergent. For example, consider the sequence extend in RU means usual metric space, where xn is equal to -1 raised to n. The subsequences sequence x to n and here is subsequence x to n of sequence xn given by x to n is equal to 1 for all n is such that x to n converges to 1 as n tends to infinity in RU. But the sequence xn is not convergent. What is remark? If a subsequence of a sequence in XD is convergent, then the sequence itself need not be convergent. Okay. For example, consider the sequence xn. xn is equal to -1 raised to n. The subsequence x to n. Here xn is equal to -1 raised to n. x to n is -1 raised to 2n. That means -1 raised to or even power of -1, and which is obviously 1. Okay. Therefore, we get x to n is equal to 1 for all n. And it is such that obviously this x to n converges to 1 as n tends to infinity in RU. But sequence xn is -1, 1, -1, 1 and so on. This is oscillatory sequence. You know that very well. This sequence is not convergent, but its one subsequence is convergent. Means this remark tells us that if subsequence of a sequence is convergent, then sequence itself need not be convergent. Let us take next theorem. Let sequence xn be a Cauchy sequence in a metric space XD. Then sequence xn is convergent if and only if and only if it has a convergent subsequence. In this theorem, we have given that Sequence Xn be a Cauchy sequence in metric space Xd. Then sequence Xn is convergent if and only if it has a convergent subsequence. Okay. First we assume that sequence Xnk be a convergent subsequence of sequence Xn, and we will prove that sequence Xn is convergent. Suppose Xnk is converges to X as k tends to infinity. Okay. Therefore, for all epsilon greater than 0, there exists a positive integer. N such that d of xnk comma x is strictly less than epsilon by 2 for all nk is greater than or equal to capital N. Also, we have given that sequence Xn be a Cauchy sequence. Sequence Xn being a Cauchy sequence. Therefore, for all epsilon greater than 0, there exists a positive integer n such that d of xnk comma xn is strictly less than epsilon by 2 for all n comma nk is greater than or equal to capital N. Okay. We have to show that Xn is a convergent sequence. Okay. That means we have to show that d of xn comma x is strictly less than epsilon. So consider this LHS. Now d of xn comma x is less than or equal to d of xn comma xnk plus d of xnk comma x, okay, which is less than or equal to, this is triangle inequality, which is less than or equal to d of xnk comma xn, because d is a matrix, plus d of xnk comma x, which is strictly less than epsilon by 2 plus epsilon by 2. This is equation number 1 and this is 2. Since by 1 and 2, which is strictly less than epsilon. Therefore, d of xn comma x is strictly less than epsilon. Therefore, sequence xn is convergent sequence. Therefore, sequence xn is convergent sequence. Okay. In converse part, we have to prove that if xn is a convergent, then it has a convergent sequence. Okay. Converse part of this theorem is same as the proof of previous theorem. Okay. We will stop here. Thank you.